So hi everyone, I'm Omid. I'm from Yahoo Research Haifa, and I'll talk about scaling cloud-scale Translytics workload with Omid and Phoenix, and it's a joint work with Jonathan Gottesman and Edward Bortnikov, both from Yahoo Research Haifa as well. Okay, so we'll start by talking about Translytics, which are basically transactions, and analytics. How can we do analytics in a transactional fashion? Then we'll see some use cases that we're doing in Yahoo to use Translytics, how we do it with HBase, Omid, and Phoenix, and then we'll deep dive a little bit talk about Omid and Phoenix and the integration that we did of Omid and Phoenix in order to have a Phoenix version that supports transaction using Omid. So let's start by a survey that was done by Lightband. Basically, people were asked which two type of application or use cases in your organization will see the biggest increase in the use of real-time data processing. Okay, and you can see the answers. Okay, most of them say that 32% actually say that AI and machine learning will be the biggest increase in the use of real-time data processing. It's not surprising, right? Because first, ML is the answer for everything currently. And also, if you're using ML and you're doing it in a real-time data processing, then your model will be more accurate. And if I'm using, for example, my model in order to do ad targeting, where ad targeting is when I want to decide which ad I want to show to a specific user, then if my models will be more updated, more accurate, then the probability, there is a higher probability that the user will click on the ad that I will show him, and it, of course, influence on revenue, and this is all about. Okay, so basically, we have here two words. The first word is OLTP, where it's actually stream processing event asynchronously being analyzed. And we're talking about that we want high latency, but we also want some data consistency. We want high data consistency, and this is not trivial. On the other side, we have the analytic word, where we want to have complex processing patterns, and we have information that arrive from many pipelines concurrently, and we need to analyze all of them. And what we actually want to do in order to do it in a real-time fashion, then we want to enjoy the best of all the words, of course, and we want OLTP and analytics all in one that will be able to do some complex analysis and to do it in a consistent fashion with low latency and in real-time data processing. And of course, as always, we want a simple API with strong guarantees. And this is why we do it with NoSQL. Okay, we want to exploit this horizontal scalability, and that's great. The problem, of course, that transitional NoSQL guarantees a row level atomicity. I have an atomicity only in one row access and not in a few rows. And all the Translytics application usually need to have a few reads and writes. For example, if I want to classify the user to a certain groups, then I want to read the user. I want to read the group data. I want to compute something, and then I want to write to each one of them, right? And for this reason, I can't have only one atomic access, one guarantee of atomic access, and this is why we need ACID. Okay, ACID was defined before in previous talks, but I'll define it as well. So what's ACID? Actually, it's late James Gray definition. Multiple data access in a single logical operation, which is atomic, which means that everything occurs or nothing occurs. Consistent means that the database switches from one valid state to a different valid state. Isolated means that it appears to execute in isolation. No one sees my changes until I successfully commit. And if I'm not, no one sees anything. And durable means that once I committed, it cannot be disappeared. Boom, it's there. Okay, so let's start by talking about the first use case that we have in Yahoo that we used Omid in is audience targeting. When a user, okay, an advertiser, upload a new advertisement to the marketplace, actually it doesn't only provide its content. it also provides a lot of metadata information and a lot of optimization information. And one of the things is, to which user do I want that will see my ad? Okay? And this is why users are divided to segments. And these segments can be from many other features. For example, age, gender, location, hobbies, browsing history, product that I purchased, and stuff like that. And user can appear in many segments, like 18 years old male that like to purchase electronic from Amazon. Okay, so what we actually want to do is we want to classify these users to segments, and then the advertiser can choose segments, and when he uploads its advertisement. Okay, and of course the timeline directly affects revenue. If you won't do it online, but we'll do it in a batch fashion, then this list will be less accurate, and we don't want to do it. So how it works? Basically, what we have a strong topology where each bolt has an algorithm, either an AI model or some rule-based rules that calculates the segments. And we have here in the storage the profile information, the user information. We have the segment information, and we also have some correlation between them. We have to know, each user has to know in which segment it appears, and each segment has to know which of the users that appear in the segments. Okay, both for analytics and also for updated different segments. And we also use some Kafka messaging. And what's important in here is that these events that are being analyzed concurrently, they can either be by the same user. If I have now a user that goes and clicks and browses the web, then I get many events from the same user. Or they can be by different user, but this different user might be classified to the same set of segments, right? Or their intersection of their segment is not empty. And I'm talking about trillions of touch points per month. People are browsing the web all the time. And these access patterns are complex. When we need to update something, we need to go to the user. We get some info from the user in order to calculate its segments. We look at the past. We look in which segment it exists, and then we decide, according to the latest event, do we want to put it in a new segment, remove it from a different segment? So we need this information. We also need to update the mapping. I have two writes, one to the segment, one to the user, maybe discarding for different segments as well. And also we want to do scans. Scans for us, both for analytics and also to go over and to decide now who are the users that I want to put the next ad to. Okay, and as I said, age-based write does not provide atomic guarantee. And this is why we use Omid for that. Okay, Omid is actually a transaction processing layer for age-based. It's a layer on top of age-based. It's an Apache incubator. Since 2015, we worked on it quite a lot. We scale it a lot. It's highly available. And we also have a version that reduces low latency. I will talk about it afterwards. And in the last 2 years, I think we worked on integrating it with Apache Phoenix. Basically, its API is very, very, very similar to NoSQL. I will show it in a bit. And it supports snapshot isolation, which is a popular consistency model. And it's working production in Yahoo for web indexing since 2015. Just that you look how to use Omid, basically, it's very, very similar to age-based, right? You see on the top we have we allocated transaction manager. That's the difference. And we allocated the T-table. T-table is very similar to H-table. I'm sure that most of you are aware of that. But in order to do that, we need to do a tm.begin to start a transaction. The transaction returns an object, tx, and then you can see we have a regular put. We just generate an age-based put. But the only difference is that when we do a put, we not only need to give the age-based put, but we also need to give the transaction object first. first we need it in order to do the right searches, and also we keep the information of all the entries that were validated for conflict analysis. And then at the end, we do a commit. The commit can either succeeded or throw a rollback exception, and then the app can decide whether we want to do the transaction again or not. Okay, this is it. Very, very simple. And that we use it for ad targeting. Another thing that we needed is to use SQL. But we want a SQL on top of NoSQL. We have HBase inside. And as you know, NoSQL API is not so easy if I want to give it to external user, maybe to computer scientists, to programmers, and simple. But if you want to give it to someone else, like advertiser, we cannot really do it. Also, it's hard to manage complex scheme, hard to implement analytics queries if I want a secondary index and stuff like that. Hard to optimize for speed, unless I want to write a coprocessor. And we also need to integrate something with relational data stores, and it was problematic. So let's talk about this use case. Basically, the use cases talks about publishing a campaign. When an advertiser want to upload the campaign to the marketplace, then it provides its context, and as I said before, optimization and other stuff that it needs to update. And it's quite a complex schema. It's not so simple. They have a lot of columns in there. And actually what we had to do is we had to give them a SQL interface, but we also needed to do other stuff. We wanted to do in our side. After they upload it, we wanted to do analytics. Okay, analytics, for example, if the advertiser upload an ad and it's reside according to the ad ID, and I want to do analytics according to the advertiser ID, so I need index for that. And if I want to go and check, for example, how many similar projects do I have for different advertisements, then I also need indexes for that. And in addition for that, we also have ML pipelines that we need to go analyze and build models for the next campaigns as well. So what we did, we used Phoenix for that after the integration, and you all know what Apache Phoenix is, right? So I'll set it fast in an OLTP and real-time analytics for HBase. Actually, it's optimized the queries to HBase calls, uses JDBC. What's nice is that it provides secondary indexes, and also it has a lot of coprocessor that does things more efficiently, and it is great. So what we did is that we did an integration of Omid and Phoenix. Basically, Phoenix is designed for public cloud scale, and Omid is extremely scalable. We're talking about more than 600K transactions per second. We also have a low latency version. It's highly available. And the release of Omid, last year we released Omid 1.0.1. It has all the features that required for the Phoenix integration. Also, we improved performance and found bugs. And in the next release of Phoenix 14.15 and its corresponding one for HBase 2.0 5.1, it will include Omid as Phoenix transaction processing. And if you like, you can use it. So what I want to do, I want to present you the numbers that we got. So we took the app that I talked before about the ad ingestion, but we did it with syntactic data due to IP issues. So what we did, we actually added 1 million entries. Okay, we just inserted 1 million entries. Each one is 1 kilobyte. Okay, and we used Omid in a sync post-commit mode. There is a async mode which is more efficient, but here it was enough. And we have here a throughput, two graph of throughput and latency. Let's take a look at the latency first. You can see we have here at the x-axis, we have here a few experiments. One does 100% inserts, the leftmost one. Then we have 90% update and 10% inserts. Then we have 100% read, that the 100% are. And then we have 100% read from an index. Okay, and you can see the y-axis show you the time, and you can see basically for 100% insert, non-transactional tables, insert to non-transaction table was around 5 milliseconds, while to transactional table was less than 6. Okay, so you're saying, okay, it's more than 5, but here we got some transactional guarantee. First, we have a consistent index that maybe after the last talk, we'll have it soon as well. But we also have the ability to do transactional with a relatively low payment. So the consistency of these two, the blue and the red, are not the same. So we're paying a little bit. There are no free lunches. But you get here more higher consistency. And also, you can write to different tables in atomic fashion and so. And also, for the 90% update and 10% insert, you can see the differences. For reads, it's a little bit more expensive because reads in Omid, it provides snapshot isolation, so we need to do a little deeper scans in order to get the right snapshot. This is not also the case. And so it's a little bit higher, but still, it's like 2 times higher. We're not talking about orders of magnitude in order to get this consistency. And in many cases, this latency is enough. For us, it's enough, and we get the consistency, which is very important. For throughput, you can see that the case is very, very similar to latency. Okay, so let's start talking about the integration a little bit. So before we started the integration, I actually asked, why do we care? Why do we need to do this integration? Why does Phoenix need a transaction manager? And the first answer for that is SQL transaction. SQL support transactions, like you can see it here. We can do a select from a table, do many operations, and then do a commit. If the commit succeeds, then everything becomes visible. If not, we're in isolation. We don't really care. So this is the first thing that why Phoenix needs transaction. Second is secondary index. Back then, at least, the index was became inconsistent a lot of time because there was a case that we actually, okay, index to, for anyone that doesn't know, index is that when I want, for example, write a key K with value v1, v2, v3, then I can create an index for that that maps one of the values to the key, for example, v1, we'll go backward, yeah, v1 in here, and then if I want to look more efficiently, I will go from the index, we'll find v1 and go to the data table. Okay, so there was a problem that in many cases, the write to the index was failed, and then the index become inconsistent. Vincent talked about it last year in his talk, and there were other, I saw that in the mailing list as well, there were a lot of discussion on this, and this was also important for that. So what we had to do in order to fix that, we had a lot more stuff, but first for indexes, we had a problem that the index was done from a coprocessor, and we didn't have information in order to handle Omid's metadata. We need to fix that. And also, the large question was how to do the on-flight index creation. Okay, when I have a table, a non-empty table, even a large table, and I'm updating this table, and now I decided that I want to do an index. Okay, the user asked to create an index. How can I create an index to the table? What will be consistent? How can I define a consistent state inside this table that I can move to the index? And also there was a problem of some snapshot isolation consistency that we had to fix in order to support absolute operations for the same table. So what about the secondary index? Let's assume that I have transactions running, T1, T2. Okay, everything is good, they're committed. We're all happy, and then T3 started running. So it started running, and then someone asked to create an index. So someone wanted to create an index, and the question is, what should I do? What should I put in my index? T1 and T2, of course, I'll take their data because they're committed, but what about T3? If it's already wrote before the create index, I don't know whether I should take this data or not, because maybe it will commit, successfully commit, maybe not. And then it continues running. Then I have other transactions that running before I completed the index. What should I do with them as well? Okay, so what actually was done is that we have two coprocessors. One is running and do a bulk put to all the transactions. Actually, it identified the state, okay, a snapshot inside the data, and it moved everything to the index. And we also had to create a fence in Omid. A fence is just a simple operation. And what it guarantees that at the point of the fence to a specific table, every transaction that started before the fence and wrote to this table will be aborted. Okay, but note, it's only at the point of the create index. There might be a case that creating the index will take days, but will abort only transactions that started before the point that the user asked to create the index. So it's a very small number of transactions. And then at this point, we also open another coprocessor that actually does take every update that is being done by different transactions and add it to the index as well. And once the create index completed, the index becomes validate, and afterwards every update will add it as well. Okay. Another problem that we have is that actually snapshot isolation definition is that the transaction read its own write. If transaction ran and it wrote, and it will read the same key, then it should see what it wrote. Okay, this is how it works. That's the definition. And what happens if we have the following case, that we are creating a table, then we're adding entries to this table, these light blue ones. But then I want to do something like that. I want to start a transaction, and I want to insert into my table every element that is in the table, but I want to increase the ID plus 10. Okay, actually duplicate the number of entries in the table, something like that. So we have a problem in here because basically what we're doing, we're reading and writing. And I want to make sure that during the insert operation, when I'm reading and writing, I'm not reading what I just recently wrote. Okay, and this is not happen according to snapshot isolation definition. And so you can say now, okay, so don't read what was after the transaction started and read only what happened before the transaction started. But what happened if I'll do another operation like this as well? I'll do another operation now, and I want to read the light blue and the blue, but I don't want to read the yellow. So what we did is that we added checkpoint that basically we can ask Omid at each stage, okay, from now on, you're reading only what was before you started this point, and everything that you're writing afterwards, you're not reading. And then we can control it. But the thing is that we didn't want to do an RPC to the transaction manager in every time that we want to do a checkpoint, because these checkpoints are also used for reverting an index update if transaction roll back. So what we did, we bound a number of allowed checkpoint. And in this case, we were able to do it at the client side, and we don't need to do any RPC for that. We decided a priority that we allowed, for example, 200 checkpoints, which is more than enough. And we can play with that. And we can do it at the client side, and it's working. Sorry. Okay. Okay, so that in terms of the integration. And I want to tell you a little bit about Omid. So Omid basically, as I said, the transaction manager. We published this work in FAST 2017. This is basically its architecture. You can see in black that it has one centralized transaction manager, which is actually the brain of the system. It lets transaction begin. The client can ask to begin. The client can ask to commit. And it does also the conflict analysis. In order to support snapshot isolation, we need conflict analysis. And also it persists the commit in the commit table. We have a metadata table that's called the commit table. And actually, it was the architecture that the transaction managers goes and wrote the commit to the commit table. And the client doesn't need the transaction manager in order to write. They can directly write to the data themselves. And the problem that we have with that is that the write from the transaction manager to the commit table was batch. In order to get high throughput, we batched the write to the commit table, and this was a problem. So what we did, and we published this work in VLDB 2018, we said, okay, instead of that the transaction manager will write the commit to the commit table, what we're doing, we're distributing these writes. So the transaction manager will get a commit request, you do config analysis, and then we'll allocate a commit ID and return it to the client, and then the client will do the commit. So we have many clients, all of them will do the commits, and we're actually distributing that. And this actually significantly reduced the latency that we got. We'll see it in a bit. We'll see the results in a bit. And that was not enough, because every production system, in order to have it in production, we have it to be highly available, right? And if we look at this architecture, then we want to look for a single point of failure, right? High availability. High available system is a simple system that does not have any single point of failure, where a single point of failure is a part of the system that if it stops working, then the whole system stops working. So let's take a look if we find here any single point of failure. So we have the client here. If it crashes, we don't care, because the commit is in the commit. The commit is persisted in the commit table. So we only have the transaction manager that's actually serving everything, and we needed to do it highly available. So what we did, we actually do a simple primary backup. We have two transaction managers. One is running, otherwise it's sleeping. It wakes up in a while, see whether it can be the leader. If it does it great, otherwise it goes to sleep for a little. And so we did this scheme. We also had some recovery state that has a leader election recipe. We did it in a way that we use leases, which are time-based lock. So we don't need many frequent accesses to Zookeeper. We use Zookeeper for the leader election. So everything is very efficient. The only thing that was problematic in here is that there might be a case that this transaction manager, both of them, think that they are the leader. There might be such an edge case, and therefore we have some split brain. So what people usually do in order to solve that, they allocate a lock that every time that the transaction manager returns an answer, then it holds this lock or write to some persisted log. It depends. And what we did some optimistic concurrency schemes, and we don't use lock, but we augment the option of the clients to forcefully abort transactions that started by other clients. And this, of course, doesn't reduce the need for locks. And we have in the mainstream execution, we ran it in a highly available mode without any overhead. Only in failover, of course, we might have an overhead, but that's OK in any case. OK, a little bit more about Omid. This is also from VLDB 2018. It's fast-paced transactions. When you're using transactional table, you always need to access using the transaction manager usually in a transactional fashion, because if you're using a regular HBase API, you might see data in there that is not visible due to isolation, that's legally not feasible. So what we did, in order to support, because many applications have single writes or single reads that we don't want to use as a transaction, because it means that we need to go to the transaction manager to begin and go to commit. We augmented Omid with the option of fast writes and fast reads. You see here we have here begin read key, commit key, begin write commit key. It doesn't important. Basically, it's a write without going to the transaction manager, read without going to the transaction manager, that still maintains snapshot isolation and in a correct fashion. And in order to do so, just in a nutshell, what we did, we added local clock for each one of the regions. We have to have two tables. We have to have local clock in each one of the table, and this clock has to be synchronized with the global clock. Okay, but we don't synchronize it all the time. We synchronize it only when transaction access the data. it goes and it updates this local clock. Otherwise, it's not needed. So there might be a case that we have some region that no one writes it for a lot of time, so the clock is not synchronized, but it's OK, we don't care, and it still remains correctly. OK, that's very in a nutshell. OK, that's just that you'll see results. So we have here in red, that's the previous Omid that I'll show you that the transaction manager does the commit. We have here in blue, that's Omid low latency that we just talked about. And we have the Omid FP, that's with the fast path of single write and single read. And you can see that the Omid FP, I don't have H baseline in here, but Omid FP is almost as HBase. Okay, it's almost like single H address. We have a little bit overhead because we need to do a few checks of the local clocks and everything in order to maintain snapshot isolation. But this is it. You can see the regular Omid, if we're not using the fast path, is still very close to the Omid FP, and the previous Omid latency is very high. It was designed for throughput oriented, but still in the new design we get very high throughput. Just you see, here we have 5 writes transactions, but in here you can see that the FP, for example, is higher. Okay, it provides worse result in terms of latency than the regular Omid, and the reason is that we have a little bit overhead. Okay, we need to do some conflict analysis downstairs at the region and not at the transaction manager, so we pay a little bit about that, but this is really negligible. Okay, so I'll just summarize. We talked about Phoenix, which is a relational database, a layer for HBase. We talked about Omid, that it needs a scalable transaction system. We talked about Omid, that is being used in YAO for many years now, and it's highly scalable, low latency. And therefore, the integration provides an efficient OLTP for Hadoop. And we also see some example of use cases in YAO that we use it for ad targeting and ad ingestion, both Omid and Phoenix. We also use Omid for web indexing. And that's it, basically. Thank you very much. I don't hear you, I'm sorry.
What version is it included in the Phoenix? I believe 5.1 now?
In Phoenix, it will be in 4.15 in 5.1. Yeah. In the next to come versions. On next or next?
And HBase 2.0 is there?
Yeah. Phoenix 5.1 support HBase 2, and it will be there. Yeah.
I can understand. Yeah. Okay. Yeah. Thanks. So I can understand. Like Omid, started maybe before or independently from Phoenix initially, but are there plans to completely integrate into Apache Phoenix as a project, or is it still planned to be a separate framework or something?
Actually, we plan to graduate it.
Graduate it.
We would like to start graduation because it's running for a lot of time, and that's the usual plan. It's running for a lot of time. Now it serves Phoenix as well, and we want to integrate it independently. Whether it will be part of Phoenix,
okay,
I don't know. Okay. Okay. Thanks, everyone. Thanks for coming.